really bad, I mean something we're going to call a logical contradiction. So even though we haven't seen all of the details yet, this should, I hope, make some sense what we're getting at. We're saying we're going to put ourselves in a situation that shouldn't happen. You might call that informally a paradox. We're going to assume the hypothesis is true, and we're going to assume the conclusion is false, which shouldn't happen. We're hoping, if the theorem is true, that that can't happen. So we're assuming something that we think can't happen, and we're showing that under those assumptions, you have some kind of logic that doesn't make sense. So for example, you might show that 1 equals 0. If you assume that P is true and Q is false, and those assumptions allow you to derive something bogus like 1 equals 0, something you know is wrong, then those assumptions must have been bad. And so the assumption that Q is false must have been bad, therefore Q must be true. So we're kind of like setting up a hypothetical like parallel universe. Suppose we're in some parallel universe where Q is actually false. Then in this parallel universe, do a bunch of logic, 1 equals 0, or 1/2 is an integer, something that makes no sense whatsoever. Therefore, this parallel universe where Q is false can't exist, so it must be true. We're going to do tons of examples today, but are there any questions about that? Okay, well, let's dive in with an example then. So we're going to start by proving the following theorem. If A is a rational number, remember the symbol Q means rational numbers or all fractions of whole numbers. If A is a rational number and B is not a rational number, then A plus B is not a rational number. So we're saying roughly, if you take something that is a fraction and you add it to something that's not a fraction, the result is not a fraction. One of those things that probably seems a little bit intuitive, but it's difficult to really figure out how you're going to prove it. So like if I did 1/2 pi, pi is not a fraction, so 1/2 plus pi also can't be a fraction. Any questions about the statement? The reason that we wouldn't try, maybe you would try, but the reason a direct proof isn't going to work out that great here is that you would assume P. So let's identify P. This whole thing here is P, and this is Q. So you'd be assuming P, which is a kind of a combination of a positive statement, A is rational, and a negative statement, B is not rational. But then you're trying to use it to prove that something is not a fraction. And normally, if you try to prove that something is not of a certain type, you end up just writing a bunch of sentences that all sound reasonable, but you just kind of argue in a big circle. Sometimes you see that I say something like that on your assignment. I say like, this is circular logic, or you're saying a bunch of things, but they don't necessarily imply anything. It's hard to argue a negative property. So a proof by contradiction will allow us to assume P is true and assume Q is false. That will turn this from a negative assumption into a positive assumption. And then what we need to do is try to work from those assumptions and find a contradiction. Find some kind of logical paradox. Okay, so let's start with our proof. So you can just say proof, or maybe a little better, you can say proof by contradiction. Any chance you have to let the reader know what kind of logic is coming up, the more likely the reader is to understand your logic. So when you're starting a proof by contradiction, you're going to use the word suppose or assume, just like normal, but you're going to point out to the reader that you are using the concept of contradiction. Otherwise, the reader is going to say, why are you assuming the opposite of the thing you're trying to prove? So one way to phrase that would be, suppose toward a contradiction, that the hypothesis is true, but the conclusion is false. Whenever you're thinking about a proof by contradiction, you should imagine that you told the reader, hey, I'm going to prove that this theorem is true. And the reader says, really, how could that be true? And then you say, well, okay, let's assume hypothetically that it's not. Let's assume that you have the hypotheses, but not the conclusion. Let me convince you that something must go wrong in this hypothetical situation. So we're assuming the hypothesis is true, but the conclusion is false. Let's translate that into some math, given what the hypothesis and conclusion actually are. So let's say this would mean A is a rational number, B is not a rational number, because that's the hypothesis. We're assuming the hypothesis is true. Then we're also assuming the conclusion is false. So the negation of A plus B is not rational is A plus B is rational. So we're assuming A is rational, B is not, and A plus B is rational. So we've kind of set up our hypothetical situation, and we're going to try to show that something must go wrong. Are there any questions so far? All right. So you might be able to start seeing where we're going with this, and if not, you will soon when we start the arithmetic. We've got a rational number, we've got an irrational number, and now we're saying that if you add them together, you get a rational number. We want to show that something must go wrong. So let's start by applying the definition of a rational number. Every time you're assuming something is rational, basically every time you want to use that assumption to write it as a fraction. So we're going to write A as a fraction, and we're going to write A plus B as a fraction. If you don't do that, then you're not really taking advantage of the fact that you have this assumption. So since A is rational, A equals, let's say, P over Q for some P, Q in the integers with Q not equal to 0. So what we've done there is we've applied the definition of a rational number to A. Now we're going to do the same thing applied to A over B. We can't use P over Q. Those letters are already accounted for, so we have to use different letters. Since A plus B is rational, A plus B equals R over S. Sum R and S in the integers with S not equal to 0. So we've got a rational expression for A, and we've got a rational expression for A plus B, and this is not part of the proof, but let me just write it so we can stare at it for a second. We're assuming B is not rational, and we're trying to find a logical problem. Does anybody have an inkling of what that might be, or see where we're going with this? Yeah. Yeah, so here's what Hannah's noticing. We've got A plus B and A as rational numbers. What do I get if I do A plus B minus A? I get B, right? Subtract off the A. Well, that's a rational minus a rational. We know from I don't know, middle school or earlier, that if you subtract two fractions, you get another fraction, right? So this is where we're leading with the problem. We've got a fraction minus a fraction, and that's going to tell us b is a fraction. But we're assuming b is not a fraction. Now we've got a logical contradiction. I'll write this all in a second, but we've got b being not a fraction, and b, that's a little confusing to say, b not being, and b being a fraction. Those are opposites. They can't both be true at the same time. Let's try to write this out, and then I'll ask if you guys have any questions. So let's say, by arithmetic, b equals, and by the way, if you're just writing out this proof for the first time, it probably isn't obvious that this is what you're supposed to do, but that's what the scratch work might help you with, and that's why you work on the scratch work beforehand. B is a plus b minus a. No surprise there. But we have fractions for each of these things. So this is r over s minus p over q. And if you remember, the way that we would subtract these is we'd have to give them common denominators. So we would take this r over s here and multiply the top and bottom times q. And this p over q and multiply the top and bottom by s. And so that's going to allow you to subtract them and get RQ, looks like QR minus PS over SQ. We're not quite done yet, but we're pretty close. We've written B, which is a thing we're assuming is not a fraction, not a rational number, as something that looks like a rational number, but we have to be careful that we actually check that it's rational. Rational says the top is an integer, the bottom is an integer, and the bottom's not 0. We have to verify that those conditions are true, and then we will know that b is a rational number. So we can say, since p, q, r, and s are integers, so are qr minus ps and sq. As long as you're adding, subtracting, or multiplying integers, you get another integer. Also, since s is not equal to 0 and q is not equal to 0, it follows that s times q is not equal to 0. It's a very important fact of arithmetic that we don't pay attention to that much, that the only way you can multiply two things and get 0 is if one of them is 0 to start with. Seems obvious. You can't multiply non-zero things and get 0, but that's an important fact. So that's what we're using here. You can't multiply two non-zero things and get 0. So we check that the numerator and the denominator are integers and that the denominator is not 0. Therefore, b is a rational number. And now is where we have found our logical contradiction. Because if we scroll back up for a second, we see that we assumed b was not rational, but we proved that b is rational. So we say this contradicts our assumption that b is not in Q. I'm going to write a little sentence of explanation. You wouldn't need to include this in your proof, but I just want to drive the point home. This is kind of an aside here. So if the hypothesis is true, then, and I'm thinking like, if the hypothesis is true, then here's another complete thought. Assuming the conclusion is false leads to a logical impossibility. This is just kind of an aside to point out once again what contradiction means. We assume the hypothesis is true. Assuming the conclusion is false led to a paradox. Therefore, the conclusion must not be false, must be true. Therefore, the conclusion must be true. And we're done. So we put our little square. So I'll go over the steps again, but let me pause here and see if anybody has questions. Okay, I'm kind of surprised there's no questions, but we'll move on and let me write out the steps as kind of a summary, and then we'll see some more examples. So here are the basic steps you follow for a proof by contradiction. Number one, assume the hypothesis is true. And the conclusion is false. Number two, and this is the hard part, do stuff. That's whatever logic it takes. In this case, it was using the definition of rational, subtracting, finding our result was rational, etc. This is where all the logic of your proof happens. Step three, reach a logical contradiction. And then at that point, you're done. Step four, declare victory. So this is how all proofs by contradiction are going to look. Now this step, number two, do stuff. Like I said, that's the hard step. That's where you're going to have to apply definitions, derive some facts, maybe do some experiments before you know how to prove it. This step of do stuff can involve other types of proof methods we've seen. For example, maybe in step two, you have to think about two different cases. That's fine, that can happen. The goal, though, is to always do something that helps you reach a logical contradiction. Anybody have questions before we do another example? Yeah, Jack. So the question, I think, was in step one, I said assume the hypothesis is true. Do you always do that? Was that the question? Oh, sorry. I just didn't hear you very well. Are you talking about up here? Are you? Yeah, so you don't need to write this block in your proofs. This is kind of me writing a little aside. But this is what contradiction, this is the outline that proofs by contradiction always take. If the hypothesis is true, and we start all of our proofs, well, most of our proofs by assuming the hypothesis is true. If the hypothesis is true, assuming, or it looks like I left out a couple words here. Maybe that was your question. I said assuming the conclusion leads. I meant assuming the conclusion is false. Left out some really important words there. Move this over here. Move this over here. Assuming the conclusion is false. Leads to a logical impossibility. Maybe that's why that was confusing. So all of our proofs by contradiction Start by assuming the hypothesis is true, then assume the conclusion is false, and then find a paradox or a contradiction or an impossibility. Those are all ways of saying the same thing. Any other questions? Okay, so now we're going to finally be able to prove a really important theorem in math, one that we've mentioned, I think. One of those rare, really important theorems that affects all of mathematics, but we will be able to prove it even in this first proof class. We're going to prove there are infinitely many prime numbers. This theorem is not just important in math, it's important in everyday life, whether you know it or not. Every time you use the internet and something is encrypted, for example, if you are logging in and putting in your password, or you're putting in your credit card number to buy something on Amazon, that gets encrypted on your computer, then sent over the wire and decrypted by the person on the other end. And that way, if somebody is tapping the wire in the middle, they can't just see your credit card number go by. The way basically all computer encryption works is with prime numbers. They take two very, very big prime numbers and multiply them together and use this in something called the RSA algorithm to encrypt your data. If there were a finite number of prime numbers, we wouldn't be able to do this. We would just list all the prime numbers, and then hackers would just try all the combinations to be able to decrypt everything. So the fact that there are infinitely many prime numbers lets you buy things on Amazon. It lets your data be encrypted. Now, one thing that looks weird about this statement is there's no hypothesis. Just a conclusion. And that's just the form that theorems take sometimes. Sometimes theorems don't have a hypothesis. They're just telling you, prove something is true. Like, for example, another proof that we'll do by probably the end of the day is that the square root of 2 is not a fraction. This is one we also mentioned. So you don't need to write this down now, but this is another theorem with no hypothesis, just a conclusion. So what this means is that when we're doing a proof by contradiction for this, we don't assume the hypothesis is true because there's nothing to assume. We just jump right to assuming the conclusion is false and try to work towards a logical contradiction. Any questions before we get started? Okay, so we start by writing proof by contradiction. We would start by assuming the hypothesis is true if we had one, but we don't, so we skip that part. And then we assume, toward a contradiction, that the conclusion is false. So assume, for contradiction, that what is the logical negation of the statement, there are infinitely many prime numbers? Yeah, Anthony? There's a finite number of prime numbers. So that's what we're going to assume. Assume toward a contradiction that there are finitely many prime numbers. So if there are a finite number of them, let's write them all out in a list. We're not going to actually write actual numbers because we wouldn't know which ones they are. This is a parallel universe where we're assuming something that's not true, but we can give them names. So let's list them in increasing order. P1, P2, P3, all the way up to the biggest one, which we'll call P sub capital N. And there's no ... to the right of this because we're assuming there are a finite number. So we're assuming there are a capital N of them. It could be 10, 100, 1,000, a million. We don't know. But we're saying since they're a finite number, we can write them out in a finite list and give them all. Okay. So the next step I'm going to do is definitely the hard part of this proof. It's the kind of thing that we would not expect you to come up with on your own necessarily. Maybe you would, but it's tricky. So the point of this proof is I'm going to explain it to you, and then hopefully you understand. Not that we would have expected you to come up with this particular proof on your own. So here's the trick. We're going to define a number. Define a number x by, we're going to take all of those prime numbers and multiply them together. So x is going to be p1 times p2 times p3 all the way up to pn, p capital N, plus 1. I'm going to multiply all of the prime numbers together and then add 1. This would not make sense if we had an infinite number of prime numbers, because if I multiplied an infinite number of these together, that wouldn't make sense. I'd get infinity. But since we're assuming that we have a finite number of them, I can multiply them all together, add 1, and I get an actual number. It could be really big, but it's definitely a number. Any questions so far? Okay. So first, observe that x is bigger than p1, x is bigger than p2, all the way up to x is bigger than p capital N. This number x that we defined must be bigger than all of our prime numbers because we multiplied them together and then added 1. So even if we only had one prime number, we still added 1, which made it bigger. So we defined a new number. Since it's bigger than our list of prime numbers, this is our complete list of prime numbers. We defined a bigger one. Therefore, x is not prime. Since x is bigger than all the prime numbers, x can't be prime. We're not done yet. This is not a contradiction. That's our first step. Let me pause here and see if anybody has questions. We took our supposed finite list of prime numbers and multiplied them all together and added 1. So what we get is bigger than all the things in that list. So x itself can't be prime. But if it's not prime, then it has to be divisible by something. Any number that's not prime is divisible by some prime number. So we can say thus, x must be evenly divisible by one of the prime numbers in our list. The logic here goes that if you are not prime means you're divisible by something. You're divisible by something, that number you're divisible by is either prime, or by the same logic, it's divisible by something, and so on. So if you pick a number that's not prime, like 110, it's got to be divisible by a prime number, in that case 2 and 5 and 11. You can take any number and you can break it down into the product of primes. But here is the key of where this plus 1 makes a difference. If I didn't have this plus 1, to ignore that for a second, then this number x, so it's just the product, this is divisible by all my prime numbers. It's divisible by p1 because it's p1 times an integer. It's divisible by p2 because it's p2 times an integer, being all of these other ones. But if I add 1, that guarantees that it's no longer divisible by any of these. For example, if I had a number that was like, let's say n equals 5k. By the definition of divisible, I know that's divisible by 5. But if I add 1, that guarantees it's not divisible by 5 anymore. If I made this something more explicit, like n is 5 times 7, that's obviously divisible by 5, and it's divisible by 7. But if I add 1, it can't be divisible by either of them anymore. So this adding 1 is the trick that ensures your new number x is not divisible by any of your existing prime numbers. Let's try to write this out now. We'd say, but by design, x is not divisible by any prime number. Because it's one more than a multiple of each prime number. And now we've reached a logical contradiction. Let me try to map out why. We formed a number x. The number itself is not a contradiction. We just formed a number. We said that number is not prime because it's bigger than our supposed list of all the primes. So x is not prime. But if you're not prime, you must be divisible by one of the primes. Except we ensured by its construction that it can't be divisible by any of the primes because it's a multiple of each prime, but then plus 1, which breaks the divisibility. So in our logical steps, we have said two opposing things. We said x must be evenly divisible by one of the prime numbers, but then we said x is not divisible by any prime number. We derived as true two statements that are opposites of each other. So this is a contradiction, and we're done. Now let me try to write out kind of an example here, and then I'll see if you guys have questions, and I assume you do. This is a pretty tricky proof. It's hard to list like an example of an assumption that you know is not going to be true in the end, but I'll try my best here. Let's suppose that 2, 3, 5, 7, 11 is the entire set of primes. Obviously, we know that's not true. We know about 13, but this is the kind of assumption towards a contradiction that you're making in the proof. The number that you would form as you are working through the logic would be x equals 2 times 3 times 5 times 7 times 11 plus 1, which is 2,311. I didn't just do that in my head. I had it written down. And this is prime. So we see in this case how we have a contradiction because we assumed we had all the primes, but then when we form x, we get another number which is prime that we had left out. So one other example. The second one follows the proof a little better. It follows the logic in the proof. What if we had said, oh yeah, we forgot 13? We assume this is the entire set of primes. Then in this case, in the logic of the proof, we would form the number 2 times 3 times 5 times 7 times 11 times 13 plus 1, which turns out to be 30,031, which is not prime, but we can guarantee by our understanding of multiples that even though it's not prime, the prime numbers that you can split it into are not going to be 2, 3, 5, 7, 11, or 13. It can't be a multiple of 2 because it's 2 times a number plus 1. It can't be a multiple of 3 because it's 3 times a number plus 1, so on. So this turns out to factor as 59 times 509. And both of those are prime. So it wasn't prime itself, but the prime numbers that it splits into are too big to be in our list. So that's our contradiction there. Okay, any questions? Try to zoom out so we can kind of see it all at once. Okay, maybe this topic is making sense. Maybe you're just not sure what your questions are yet, which is fine. We'll figure them out later. You can always ask, email, office hours, whatever. We've got about 8 minutes left, so I think that's going to be enough time to prove the last example that I want to hear. Here's our last theorem, our last example, the proof by contradiction section. And I mentioned this earlier. We're going to prove the square root of 2 is irrational. And I mentioned a couple weeks ago the legend about this fact that comes from the ancient Greek cult or religious order called the Pythagoreans, and named after Pythagoras, of course. Among their many beliefs, one of them was that every quantity in the universe could be written as a fraction of whole numbers. They didn't exactly have that terminology, but that's what it boiled down to. And then one of them proved that with basically the proof that we're going to do, that couldn't be true for the square root of 2. It couldn't be written as a fraction of whole numbers. And depending on your source, they either kicked him out of the cult, or they threw him off a cliff, or they buried him alive, or something terrible, because he claimed something that went against their beliefs. Okay, so the proof is not that complicated. You can kind of see how somebody would have been able to come up with it in ancient Greece. We just have to think through a couple steps carefully. So here's our proof by contradiction. Just like in the last case, there's no hypothesis here, just a conclusion. Before I state that, let me just remind you what square root of 2 means. I think we all know, but it's useful to see it. Square root of 2 means the positive real number, r, such that when you square it, you get 2. When we say square root of 2, that's what we mean. The number that if you square it, you get 2. So we're going to assume the opposite. We're going to assume square root of 2 is rational and try to find a problem. Assume toward a contradiction. That the square root of 2 is rational. Then we can conclude that there are integers a and b with b not equal to 0, such that now what you would normally think that I was going to write here is we could assume there are integers such that square root of 2 equals a over b. And I am going to write that, but we can actually assume even a little bit more information about these integers, and normally we don't because it's useless to us in a lot of applications, but we can assume a little bit more here, and we're going to need it. So we're going to assume, number 1, square root of 2 is a over b. That's the obvious part because we're assuming it's a fraction. Number two, we're going to assume that a and b are both greater than 0. Normally, this wouldn't help us. It wouldn't make a difference. But if I'm going to make a fraction for a positive number, I know that I could do positive over positive or negative over negative. I know that I have multiple choices. So I'm saying here specifically pick the one that is positive over positive. We know there is some option. That's the one we're picking for A and B. And number three, kind of along the same lines, we're going to assume A and B share no factors. Meaning they are in reduced terms. This is, again, something we normally don't assume when we're applying the definition of rational because it just is of no use to us. But if I say I'm going to write something as a fraction, I can always assume that I've been extra smart and written it in reduced terms. So if the number was 2/3, 0.666, whatever, repeating, I know that I could write that as 4/6 or 2/3. And I'm saying let's just do it the efficient way and write it as 2/3. So this is the part that seems a little weird the first time, but it basically says if we have something that's a fraction, there's some way to write it as a/b in reduced terms and with positive numerator and denominator because it's a positive number. So we know these three assumptions are true. And so I'm running low on time, so I'm going to go kind of through the arithmetic here. The book lays out all of the details. So if I go a little too fast, you can just check out the book and fill in the gaps. Here's how we can apply these assumptions. We have the square root of 2 equals a/b. I'm not going to write out all of the filler words here just to save some time. I'll just kind of write it like we would with our scratch work. I can multiply the b over to the other side, and I get a equals times the square root of 2. And then I could square both sides. So square both sides, I get a squared equals 2 times b squared. So that's just arithmetic, nothing too surprising there. But what does this mean? This means a squared is even. It should not be obvious to you yet where the contradiction is going to come from. This is one of those proofs that would be hard for you to come up with on your own, but once you see it and have some time to digest it, it should make sense. We had a theorem that said if a squared is even, then a is even. I think it was n when we proved it. If n squared is even, then n is even. And if n squared is odd, then n is odd. We did that back in 2.1 or 2.2. So if it's even, let's write it as 2k. Okay, so far, no contradiction. Well, let's take this 2k and let's plug it in to here. So that means that 2k squared equals 2 times b squared. We're almost done, I promise. We square that out. That's 4 times k squared equals 2 b squared. And let's divide out the common factor of 2. 2k squared equals b squared. So now this means b squared is even. And by that exact same theorem, if b squared is even, then b is even. And you might not notice it at first, but this is where we've reached a logical contradiction. If I can zoom out a little bit here, we assumed a and b share no common factors, but we said b is even and a is even. So that means they share a factor of 2. And that's a contradiction. So I had to rush a little bit there at the end, but the book has the exact same proof. It's important that you spend a little bit of time digesting it and understand the steps. When you do the suggested homework for this, which you'll probably do after the exam since this isn't on it, there are questions that require arguments like this. So now that you've seen it, you should be able to, with some practice, replicate it in other questions. Any questions before you guys all take off? Okay, I will see you on Friday for the exam. Remember, I have office hours Friday morning, and email me if you have any questions.
Have a good day.
Thank you.